Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual landscape of the early 20th century, a period of ferment where the classical edifice of physics was being profoundly reshaped by the twin revolutions of relativity and quantum theory, two fundamental enigmas persisted with remarkable stubbornness. The first concerned the essential nature of the X-rays discovered by Wilhelm Conrad Röntgen in 1895. These mysterious emanations, capable of penetrating flesh and casting shadows of bone, defied easy categorization. A vigorous debate raged between proponents of a particle hypothesis, championed by figures like William Henry Bragg, and those who argued for a wave nature, a view advanced by George Stokes and supported by Charles Barklay's early polarization experiments. The second enigma lay hidden within the silent, geometric beauty of crystals. For centuries, their exquisitely regular external forms had hinted at an equi-ordered internal constitution. Theorists such as August Bravais, Leonhard Sonck, and Arthur Schonflies had developed a sophisticated mathematical architecture of possible spatial lattices, yet these remained elegant, unproven geometric abstractions. In 1912, within the vibrant scientific milieu of the University of Munich, Max von Laue conceived of an experiment of breathtaking conceptual simplicity that would, in a single stroke, resolve both quandaries. His subsequent discovery of the diffraction of X-rays in crystals constituted a moment of supreme synthesis, simultaneously confirming the wave nature of X-rays and the lattice structure of crystalline solids, thereby providing humanity with a key to unlock the atomic architecture of matter itself. The intellectual ground for Laue's breakthrough was prepared by decades of seemingly disconnected inquiries. The failure of physicists to observe X-ray diffraction using conventional ruled gratings was a primary piece of evidence for the particle camp. For the wave theorists, this negative result simply implied that if X-rays were indeed electromagnetic waves, their wavelengths must be extraordinarily short, far smaller than the finest spacing achievable with mechanical means. The necessary scale for a suitable diffraction grating was on the order of angstroms, a dimension tantalizingly close to the estimated size of atoms. Concurrently, the world of crystallography was a domain of pure form and mathematical symmetry. The 14 Bravais lattices and the 230 space groups of Sonck and Schonflies described every possible way that points could be arranged periodically in three-dimensional space. This body of theory was a masterpiece of deductive reasoning, a complete and self-contained system. Its connection to the physical reality of atoms and molecules was, however, entirely speculative. It existed as a Platonic ideal awaiting empirical incarnation. The stage was set for a mind capable of seeing a connection between the impossibly small scale of hypothetical X-ray waves and the equally hypothetical atomic regularity of crystals. The catalyst for this connection arrived in a moment of serendipitous intellectual exchange, a scene that has since become lore in the history of science. In the early months of 1912, Max von Laue, then a private docent under the formidable Arnold Sommerfeld in Munich, was engaged in conversation with a doctoral student, Paul Ewald. They strolled through Munich's Englischer Garten as Ewald described a problem from his thesis concerning the propagation of light through an anisotropic, periodic arrangement of resonators. Ewald was investigating the behavior of optical waves with wavelengths much larger than the spacing of the resonators in his theoretical crystal. It was at this moment that the decisive question formed in Laue's mind: what would happen if the wavelength of the radiation were much smaller than the spacing of the scattering centers? The thought was an electric spark. If the interatomic distances in a crystal were on the order of angstroms, and if the wavelength of X-rays was of a similar magnitude, then a crystal should behave as a natural, three-dimensional diffraction grating. The atoms themselves, arrayed in their perfect lattice, would provide the periodic structure necessary to scatter the waves in a coherent, predictable pattern. This profound insight, born from a casual conversation about a different problem, was the theoretical core of the discovery. The execution of the idea fell to two of Laue's more experimentally adept colleagues, Walter Friedrich and Paul Knipping. Their initial skepticism gave way to scientific duty. The experimental apparatus was strikingly simple. An X-ray tube generated the radiation, which was collimated into a fine beam by a series of lead screens. This beam was directed at a small crystal of copper sulfate. Behind the crystal, a photographic plate was positioned to capture any radiation that passed through or was scattered. After several attempts and adjustments to the setup, in April 1912 they developed a plate that changed the course of science. The image revealed a large central spot caused by the main, undiffracted X-ray beam. Surrounding this central point, arranged in a pattern of beautiful, halo-like symmetry, was a constellation of smaller, distinct spots. It was the diffraction pattern Laue had predicted. Each spot was a point of constructive interference, a silent testament to the wave nature of the incident radiation and the periodic, lattice-like arrangement of the atoms within the crystal. Laue immediately set to work on a rigorous mathematical description of the phenomenon. He understood that for constructive interference to occur, the path difference between waves scattered from adjacent atoms in the lattice must be an integer multiple of the wavelength. This condition had to be met simultaneously in all 3 dimensions of the crystal lattice. This led to his formulation of the 3 famous Laue equations for a crystal lattice defined by the basis vectors A, B, and C, and for an incident X-ray beam with direction cosines alpha 0, beta 0, and gamma 0, a diffracted beam would be observed in a direction with cosines alpha, beta, and gamma only if the following 3 conditions were satisfied. First, the product of the lattice constant, and the quantity, cosine of alpha minus cosine of alpha 0 equals h times lambda. Second, the product of the lattice constant, b, and the quantity, cosine of beta minus cosine of beta 0 equals k times lambda. And third, the product of the lattice constant c and the quantity, cosine of gamma minus cosine of gamma 0 equals L times lambda. In these expressions, lambda represents the X-ray wavelength, and h, k, and L are integers. These equations formed a direct mathematical bridge between the macroscopic geometry of the spots on the photographic plate and the microscopic geometry of the unit cell of the crystal. For the first time, an observable pattern could be directly translated into knowledge about the arrangement of atoms, a realm previously inaccessible to direct observation. The publication of these results, in June 1912, sent an immediate and powerful shockwave through the international physics community. The evidence was irrefutable. The ordered pattern of spots could arise only from the diffraction of waves by a periodic structure. The dual mysteries were solved in one elegant demonstration. The swiftness of the discovery's acceptance is measured by the awarding of the Nobel Prize in Physics to Max von Laue a mere 2 years later, in 1914, a remarkably rapid recognition of its fundamental importance. The work's immediate influence was most profoundly felt by the father and son team of William Henry and William Lawrence Bragg in England. While Laue's equations were mathematically robust, they were somewhat cumbersome for practical analysis. The younger Bragg, William Lawrence, possessed a flash of intuition equal in its brilliance to Laue's. In 1913, he realized that the complex phenomenon of 3-dimensional diffraction could be reconceptualized with stunning simplicity. He envisioned the process as a form of reflection of the X-rays from parallel planes of atoms within the crystal lattice. This insight led to the formulation of Bragg's law, a single, powerful equation n times lambda equals 2 times d times the sine of theta. Here, n is an integer representing the order of reflection, lambda is the wavelength, d is the perpendicular spacing between the atomic planes, and theta is the angle at which the X-rays strike these planes. This elegant simplification transformed X-ray diffraction from a profound physical demonstration into a versatile and powerful analytical tool. It was this simplification that truly inaugurated the field of X-ray crystallography, allowing scientists to move from confirming the existence of lattices to precisely determining their structure. The legacy branching from Laue's Munich experiment is vast and transformative, extending into nearly every corner of the physical and biological sciences. Armed with Bragg's law, the Braggs themselves quickly determined the first crystal structures, beginning with simple ionic compounds like sodium chloride, revealing its interlocking face-ended cubic lattice and providing the first direct visual evidence of ionic bonding. This opened the floodgates. Throughout the 20th century, X-ray crystallography became the definitive method for mapping the atomic world. It elucidated the structures of metals, alloys, and minerals, providing the fundamental basis for modern materials science and engineering. In chemistry, it revealed the precise 3-dimensional shapes of organic molecules, confirming the tetrahedral carbon atom of Van't Hoff and unlocking the secrets of stereochemistry. The technique empowered chemists to understand reaction mechanisms and design new molecules with tailored properties. Perhaps its most profound impact came in the burgeoning field of molecular biology. The intricate structures of complex biological macromolecules, which held the very secrets of function, became accessible. Dorothy Hodgkin's noble-winning work deciphering the structure of penicillin and later insulin provided a blueprint for understanding their biochemical activity. The ultimate triumph of Laue's legacy arrived in 1953. The ghostly X-shaped diffraction pattern in Photo 51, an image produced by Rosalind Franklin and Morris Wilkins, provided the crucial clue that allowed James Watson and Francis Crick to deduce the double helical structure of deoxyribonucleic acid. That faint pattern of spots was a direct intellectual descendant of the symmetric constellation captured on Laue's photographic plate 4 decades earlier. Seeing the architecture gene itself was made possible by the technique that first allowed humankind to see the architecture of a simple salt. In conclusion, the 1912 discovery of X-ray diffraction by crystals stands as a paragon of scientific inquiry, a perfect confluence of theoretical prescience, serendipitous discussion, and careful experimental execution. Max von Laue's contribution was a supreme act of intellectual unification, forging a link between the physics of radiation and the geometry of matter. The result was far more than the confirmation of two working hypotheses. It was the invention of a new form of vision. It provided a methodology, a powerful light, with which to illuminate the invisible submicroscopic world where atoms arrange themselves into the ordered structures that constitute our reality. The legacy of those first diffraction spots is a testament to the power of a single, well-posed question, from the initial conformation of waves and lattices to the intricate folds of proteins and the elegant spiral of life's code. The ability to map the atomic realm stems directly from that foundational moment in a Munich laboratory, forever changing our understanding of the material world and our place within it.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.